So hello everyone, we are discussing this problem from CP-31 sheet that is almost equal, make almost equal with mod. And in this problem, we are given an array n of size n with distinct integers. It means all the integers present are different, and we are allowed to do an operation exactly one time. In that operation, we'll have to choose an integer k and then just replace all the elements present in the array with ai is equal to ai percent k. मतलब we have to replace them with the mod that is given when we divide by k. So we can choose the k from 1 to 10 raised to 18. That means that would be 2 raised to 64 if we convert. And after we are done doing this, we should have two different values. So initially we had n different values in the array, and after doing the operation, we must have two different values. And it is also said that such an answer always exists. So there is always an answer, and if there are multiple answers, you can just print any of them. So let's discuss it. And before exactly moving to the or towards the solution, we can just look at the constraint that is given to us. N is from 2 to 100, so we can just run a pretty n cube or n cube log n type of solution, because n cube log n will be hardly 10 raised to 6, and that can run in 1 second. So also we are given with the AI values. They are ranging from 1 to 10 raised to 70. Okay. So the first thing that should come to your mind, or that comes to my mind after reading the question, is that any number that gives only two remainder is 2. 2 is the only number that can give two reminders, that are 1 and 0. But in order to get both these reminders, we must have a combination of odd plus even numbers. If the array has one odd and n minus one even numbers, or any combination of odd and even numbers, then 2 is always the answer. But if the array only has odd numbers, then 2 is not the answer. Also, if the array only has even numbers, then also 2 is not the answer. Why? Because all the even are divisible, so they will give reminder only 0, and it wants you to have a reminder, two different reminders. So, 2 won't be the answer always. Also, one other new thought that can come to your mind is that why we can just take all the numbers from 1 to k, 1 to 10 raised to 18, and then just run it in a loop. So this is also clear that you can't run a loop from 1 to 10 raised to 18 in 1 second and just check for each. This is also not possible. So these are two naive cases that can come to your mind but are not possible. So what is the solution? I am actually starting with a claim. I am claiming that, let's say you have a binary representation. Let's suppose you have binary representation of all the n elements. You have the binary representation of all the n elements. I am claiming this point that for the ith bit, I am claiming this point that for the ith bit in binary representation of all the elements, that is different. That is different. Ith bit is what? It is the smallest. It is the smallest bit from the leftmost side. It is the smallest bit that is different in each. That is different in each number's binary representation. Then my answer would be 2 raised to I. Why so? Let's see that. What I am claiming first, I just want to make it clear. Let's suppose this is the binary representation of. Here we can see that. Here we can see that first two bits are same. First two bits are same. The third bit. The third bit is different in each. Here it is 0. Here it is 1. Here it is 0. Different in each. By saying different in each means it is at least different in one. I want to say that it is at least different in one element. At least different in one element. Ith bit means what? It is the smallest bit that is at least different in one element binary representation. So here we can see that it is different in the third. It is different in the third. So our answer would be 2 raised to 3. Now why this will be our answer, that can come to your mind. So first of all, why this is our answer? So for any number, let's say we have any for any power of 2, 2 raised to x, what reminders it can give? It can give reminders from 2 raised to x minus 1 to 0. It can give these reminders. That is so pretty easy. Like for any number n, it can give a reminder from n minus 1 to 0. Now, for any power of 2, what exactly constitutes the reminder? Like what exactly produce the reminder? Let's just discuss that. So let's suppose these are the binary representation. Oh, okay. These are the binary representation, and if I divide this number by 2, 2 raised to 1 basically, then 1 means first bit. The for any uh, for any power of 2, let's suppose there is a number n, and then in its binary representation, if I divide that number by ith power of 2, then the remainder will be nothing else but the binary representation of I to first bit. This is pretty understanding, right? What I'm trying to say is, I have this number, and if I divide this number by, let's say, 2, that is 2 raised to 1, then my remainder will be always given by the binary representation of ith to first bit. So here the binary representation of ith to first bit will be nothing else but this number only, and this will give me what? This will give me 1 into 2 raised to 0. My remainder would be how much? 1. You can check this for other numbers as well. Let me show you this thing for other examples as well. Let me choose 2 raised to 3. Okay, just let's first see what this number is. I am making this number smaller for easier understanding. Now this number is 7. 3 ones means 7. And if I choose to divide this by 2 raised to 3, then what will be our remainder? 2 raised to 3 means 8. Then we know that 7% 8 will be 7 only. So if I divide 7 by 8, then the remainder I am going to get is obviously 7. Why? Because we had 2 raised to I as 3, then the remainder will be the binary representation of I to 1. The binary representation of third to first is 7 only. We can take another example, 1, 1, 1, and then we have, let's suppose if I divide it by 2 raised to 2, then the remainder must be binary representation of 2 second bit to first. That is this. This means what? 2 raised to 1 into 1 plus 1 into 2 raised to 0. That is 3. So the binary representation gives us 3. So this concept is also really clear, like, and it's also easy to understand that whenever you divide a number n by some, say, 2 raised to I, then the remainder is given by binary representation of first bit to ith bit to first bit. This gives us the remainder in this case whenever we do such divisions. Now let's just get back to the main point that we were discussing before. Wait a second. Okay. So that was also obvious that whenever we divide n with 2 raised to I, then the remainder is decided by the binary representation of ith to first bit. Okay. Now, then the remainder is decided by 2 raised to n% 2 raised to I. Now, let's why I am claiming this answer, that if I is the smallest bit, that is smallest bit from left, that is different in each of, that is different in at least any of the array's element. That means here here I can say that the first bit is different in at least one. Here it is 0, here it is 1, here it is 1. So my claim is that my claim is really simple. I am saying that the first bit that is different in at least one, it can be in different in more than one. For some it should be 0, for some it should be 1. I mean, let's say for the at the third place at the third place in the first and first, second and third element. Let's suppose if your array has 5 elements, then in the third bit of the first, second and third elements, I have 1, and in the this fourth and fifth bit I have 0. So this is something I'm saying, this is something I'm claiming, that whatever be the ith smallest bit that is different in at least one will be our answer, will be our k. Now, why this claim works, that ith smallest bit from the leftmost, which is different in at least one, is the answer. Why it works? That let us see that. Let's suppose I have the. Acha, what will be the binary representation look alike in them? I don't care about what is after what is after ith position in all of the binary representation, and I also don't care about what is before, because because after I don't care for some other reason, before I don't care for some other reason. Why I don't care about before? Because I is what? I is the smallest position that is different in all other. That means that means before I, all the bits are same in all the numbers. That means all the bits are same in all the numbers. Let's say this is I, then this much representation of all the bits will be same. Do you agree to this? This much part of all the bits will be same. You don't have to think about it. And why not to think about this? Because this can never be our remainder, since we are dividing by 2 raised to I, which can give a remainder of 2 raised to I minus 1, 2, 0. This can only be the remainder, okay? So we just don't have to think about what comes after I in the binary representation of all the numbers. So let's just get back to the solution again. And we claim that, not claim, we just prove that this much part will be same in all the arrays element. If this much part is 1 0 1 0, it will be 1 0 1 0 for all, not just for one. It will be same for all. So only different part would be this. Now, since this is the binary representation, then what can be this? This can be 0 or 1. So let's say for an array of element n, for some element this ith position is 0, for some element ith position is 1. So I am claiming that these all zeros will produce a remainder of x, and these all ones will produce a remainder of y when divided by 2 raised to I. Why? That should come to your mind, that why. So if I, as I said, the remainder will be what? For any number n, the remainder is what? When you divide them by 2 raised to I, the remainder is simply the remainder is simply what? The remainder is simply binary representation of I to 1. That is so pretty clear. So reminder in this case will be binary representation from this to this, and the reminder in this case also will be binary representation from this to this. So let's suppose if I assume I, then all these are the same. I'm assuming, let's say for this example case, I'm taking all of them to be 1 0 0, and then the remainder will be this only. So if I divide them by 2 raised to I, the remainder will be binary representation of this I to this ith position to the first position. So and how we write the binary representation? We write it like this: I into 2 raised to I minus 1 till 1 into whatever it is, means whatever the value is, 1 or 1. For this particular case, it is, we can see over here it is 0. So we can just write out it over here: 0 into 2 raised to 0. Okay. Okay, 2 raised to 0. So as we know that this part is same for all, so let me assume this part to be p. Then for some set of numbers, it will be I into let's say that the same part is this. Okay, let's suppose over here it is x. This is x. X can be simply either 1 or 0 at the ith place. Since it is a binary representation, so it will be either 1 or 0. So this will be x into 2 raised to I minus 1. Okay. Now, for some, this will be 1, and for some, this will be 0. Rest p is same in both. So for one case, let's suppose when it is 1, when our x is 1, then what it will look like? Then the remainder will look like this: p plus 2, uh, p plus 2 raised to I minus 1. And so it was 1, then it will look like this. So for all the elements where the ith bit was x is equal to 1, for them the remainder is this. Now for all the cases where x was 0, for them the remainder will look like this: 2 plus I minus 1 into 0. That means p. So you can see that for all those numbers we have got the remainder. For all those numbers where the ith bit is 1, we have got the remainder p plus 2 into I minus 1. And for all those places where the x was 0, where all the ith bit was 0, there we have got the remainder as p only. So we have got two different reminders for the specific 2 raised to I. Hence, we have proved this thing that whenever we find the ith smallest bit that is different in at least one of the element of the array, then we are going to get a reminder. We are going to get two different reminders. We have proved this thing. So how to do this thing in code? We can just simply, we can just simply loop from 1 to, we can loop from 1 to 64 and generate powers of 2 and generate powers of 2, and then just we can loop from 1 to n in the array and find such 2 raised to I, find such 2 raised to I where I is the different bit, where I is the first different bit, first unique bit, that is at least first such bit that is at least different in one element, at least different in one element. It can be different in multiple elements. Multiple can have 1 at the ith place and multiple can have 0 at the ith place. All having 1 will produce this remainder, and all having 0 will produce this remainder p. So and how we can just keep a track of it? We can simply create a map, and for 2 raised to I we can store all the reminders in this map. For 2 raised to I we can store all these reminders in map, and at the end we can just check if the size of the map is 2 or not. Map has a size of 2, that means what? Map has a size of 2, that means simply that uh, there are two different reminders that are stored. So if the map has a size of 2, then the answer for k is equal to nothing else but 2 raised to I. You can just break it over it. The code is really simple. There is nothing really complex in code. We just had to understand first that first part that was important that we had to understand was whenever we divide any number n by some 2 raised to I, then the remainder is given by the binary representation from I to 1 in the end. This is something that we had to understand, and then just we can see that when we divide it by 2 raised to I, let's suppose the ith position has element x. X can be nothing else but 1 or 0. For the cases where it is 1, there the remainder will be p plus 2 I minus 1, and the for cases where x is ith position is 0, there we will have remainder as p. So we got two different reminders for such position. That is simple. And how to implement this whole in code? We can simply just run a loop from 1 to 64, generating powers of 2. And why 1 to 64? Since we are asked to check for 2 and raised to 17 kind of numbers, so we can just check till 64. That will be enough. 2 raised to 64. That will be enough. So this was easy. We can just keep a map and keep the count of all the unique. You can keep a map. You can keep a set, whatever you want. At last, just you have to check the size of set or map. So let's just look at the code once. Here is the code that we have. See, we are running a loop from 1 to 64, and then just we are generating power of 2 by shift operations, and then I have used unordered map, and then just stored the percent n, then stored the remainder in each case, that is from 0 to n, and then just have checked this thing ki the size of the map is 2 or not. If the size of the map is 2, then that particular power of 2 is my answer. The code is really simple. I hope you understood it easily.